before I explain anything, listen to this. That sound was recorded in 1997. The equipment that caught it was built to detect nuclear explosions. It was sitting on the seafloor of the Pacific Ocean, and it picked up something that had nothing to do with any weapon, any ship, or any submarine. Multiple sensors, thousands of kilometers apart from each other, all recorded the same event at the same time. Scientists analyzed the frequency signature. They found something that made the room go quiet. The shape of the sound wave was biological, meaning whatever produced this was alive. But the acoustic energy required to be heard across 5,000 kilometers of open ocean pointed to a creature larger than anything in the scientific record. The blue whale, the largest animal on Earth, cannot come close to producing a sound this powerful. For a moment, researchers thought the ocean had recorded something enormous, something unknown. They called it Bloop. For 18 years, nobody had an answer. Then the answer came, and it was stranger than any animal. It wasn't a creature at all. It was ice. A frozen continent, 14 million square kilometers of it, cracking under its own weight. Loudly enough for the ocean to carry that fracture across 5,000 kilometers of open water and deliver it, still recognizable, to a sensor on the other side of the Pacific. Not a monster. A continent, speaking. And the ocean transmitted that sound as cleanly as a telephone call. That's what this video is about. Not just Bloop. The ocean contains dozens of recorded sounds that still have no confirmed explanation. It contains a whale that has been calling at a frequency no other whale can hear for over 30 years, with no response from anything alive. It contains a sound called Upsweep that returns every spring and autumn like clockwork, and has done so since 1991, with no identified source. It contains the acoustic record of underwater volcanoes, collapsing icebergs, and geological events that no surface observer ever witnessed. The ocean has been producing, transmitting, and recording sound for hundreds of millions of years. We built equipment sensitive enough to hear it 80 years ago. What we've heard since, and what we still can't explain, is what the next hour covers. At around 1,000 meters depth, something happens to sound. The temperature and pressure at that level combine in a precise way that traps sound waves inside a narrow horizontal band. Waves above bend downward toward it. Waves below bend upward toward it. Anything entering that layer has nowhere to go except sideways, across the ocean, for thousands of miles, losing almost no energy as it goes. This layer is called the SOFAR channel. It's a long-distance sound transmission system built into the physics of the ocean itself. No one designed it. It's been there since the ocean took its current form, and it operates at a scale that is genuinely difficult to absorb. A sound entering the SOFAR channel near New Zealand can reach a sensor near Iceland. The same channel, the same sound. The discovery came in the 1940s. American researchers dropped small explosive charges into the ocean near the Bahamas. Hydrophones positioned off Bermuda, 900 miles away, picked them up clearly. They moved the sensors further, still clear. They tested across the Atlantic, still detectable. The physics worked exactly as the calculations predicted. The implication was immediate, and the military understood it before any scientist could publish. If you put listening equipment inside the SOFAR channel anywhere in the ocean, you could, in principle, hear almost anything happening anywhere else in the ocean. They started building. Through the 1950s and 60s, the U.S. Navy laid thousands of miles of hydrophone cable across the Atlantic and Pacific seafloors in total secrecy. The network was called SOSUS, Sound Surveillance System. Shore stations ran around the clock. Analysts sat with headphones, listening. The target was Soviet submarines, and the network found them, tracking acoustic signatures across entire ocean basins with enough precision to identify vessel class from propeller sound alone. But the analysts were hearing everything else too. Whale calls, arriving from thousands of miles away with startling clarity. Underwater earthquakes, triangulated to locations no surface observer had reported. The cracking and grinding of polar ice sheets. Volcanoes on the deep seafloor that no ship had ever surveyed. Every acoustic event large enough to enter the SOFAR channel was flowing through the same cables built to catch submarines, and the analysts wrote down everything they couldn't classify. When the Cold War ended, the network was partially declassified. In the early 1990s, access was handed to civilian researchers at NOAA, the National Oceanic and Atmospheric Administration. Those researchers found themselves holding something they hadn't expected. Decades of continuous deep ocean recordings made by the most sensitive listening equipment ever deployed, covering a period when no civilian program had been paying attention to the ocean at all. They started going through the archive. Within a few years, they had a problem. The ocean had been making sounds that matched nothing in any scientific record. Not geological, not biological, not mechanical. Sounds with no category, no source, no explanation. They built a catalog. They gave each sound a name, and some of those names are still open files. Here is what that catalog contains. There are 5 sounds in the NOAA archive, recorded, analyzed, and published, that have never been definitively explained. Each one has a name. Each one has a known location. Each one has been studied by researchers for years or decades. None of them has a confirmed source. Some of them are still being recorded right now. Upsweep. First detected in August 1991, shortly after NOAA gained access to the network. A narrow, sustained tone that sweeps gradually upward in pitch over several minutes, then stops. Multiple hydrophone arrays across the Pacific detected it simultaneously. Source triangulation pointed to a region of underwater volcanic activity near the Pacific Antarctic ridge. It comes back every spring and every autumn. It has been recorded, without interruption, every single year since 1991. Nobody knows what makes it. Julia arrived in March 1999, lasting about 15 seconds. When slowed to a range human ears can process, it sounds, and researchers have noted this in published descriptions, like a voice. Rising, then falling, with a shape that reads as almost conversational. Triangulation placed the source in the Antarctic region. No geological event was registered on that date. No biological source has been confirmed. Julia has never been recorded again. One sound, 15 seconds, 30 years of no explanation. Train has been in the archive since 1997, a constant low-frequency signal with almost no variation in intensity or character, like something mechanical moving at a steady, sustained pace. Source triangulation placed it in the equatorial Pacific. Multiple hypotheses have been proposed, none confirmed. Slowdown was recorded in May 1997, lasting approximately 7 minutes. What makes it strange is the pattern. The frequency of the sound decreased uniformly across the entire duration. It started higher and descended steadily, all the way to the end. Whatever produced that sound was changing in some measurable physical way for exactly 7 minutes and then stopping. The mechanism that would cause this has not been agreed upon. Then there was Bloop. And Bloop was different from all of them, because Bloop carried a biological signature. Sound is the ocean's native language, not light. Light dies within a few hundred meters of the surface, not radio waves. They can't penetrate salt water at all. Sound moves through water roughly 4.5 times faster than through air, and it loses far less energy doing so. In the deep ocean, sound doesn't just travel. It propagates across distances that have no equivalent anywhere on land. The SOFAR channel works because of a property called refraction. Sound bends toward wherever it travels more slowly. Cold water slows sound. High pressure speeds it up. At around 1,000 meters, those two forces reach a balance point that creates the minimum speed in the entire water column. Sound entering from above bends downward toward it. Sound entering from below bends upward toward it. Both converge on the same layer and travel forward, trapped, with almost nowhere else to go. The numbers make this tangible. Sounds from underwater nuclear tests have been detected on the opposite side of the Earth via the SOFAR channel. The 1960 Chilean earthquake, the largest ever recorded, sent acoustic signals through the ocean that circled the globe multiple times, still detectable hours after the initial event. A volcanic eruption on the East Pacific seafloor leaves an acoustic fingerprint on hydrophone arrays in the North Pacific within hours of happening. The ocean is not a passive body of water sitting between continents. Acoustically, it is a planetary-scale transmission network that has been running continuously for hundreds of millions of years, carrying sounds from every earthquake, every eruption, every large animal, every shifting iceberg, to every corner of the ocean simultaneously. Until 80 years ago, none of it had an audience. The SOFAR channel covers roughly 70% of the Earth's surface. That's the surface area of the ocean. And at 1,000 meters depth across that entire surface, there is essentially one connected acoustic space. A sound produced near New Zealand enters the same channel as a sound produced near Iceland. Given enough intensity, they can interfere with each other. Events in the Antarctic reach hydrophone arrays in the Aleutian Islands. The ocean doesn't experience sound the way a room does, where a sound at one end is separate from a sound at the other. At SOFAR depth, the ocean hears everything at once, everywhere simultaneously. This is why SOSUS could track Soviet submarines from a relatively small number of shore stations. It's also why Bloop, a single event somewhere in the Antarctic, was simultaneously detected by sensor arrays separated by 5,000 kilometers. The network didn't need to be in the right place. In the SOFAR channel, there is no wrong place. Researchers who work with this data regularly describe the experience as spatially disorienting. A blue whale somewhere south of the equator can appear, on a North Atlantic hydrophone, to be just outside the recording station. The ocean collapses distance in a way that human experience has no framework for. When NOAA scientists gained access to the SOSUS archive in the early 1990s, some of their early work involved simply identifying what the Navy had unknowingly collected. Migration routes of whale species appeared in the data. The same individual animals, identified by call pattern, tracked across thousands of miles as they moved through the ocean. Entire populations of blue whales showed up in locations where scientists hadn't known they existed. Events that marine biologists had spent years trying to document from research vessels were already recorded in full detail in classified military archives. The ocean had been keeping a record of its own acoustic life. Nobody outside the Navy had known the recording was running. Every anomalous sound in the NOAA catalog, every whale call archived in SOSUS recordings, every geological event that left an acoustic fingerprint, they all share one feature. They were produced by the ocean acting on itself, long before any human being was in a position to hear them. The SOFAR channel existed and functioned for hundreds of millions of years before the first Navy hydrophone was placed in it. Whales evolved their long-range calls specifically because the channel was already there. They learned, through evolution, to put their voices into the most efficient transmission medium on the planet. Geological events produced sounds that traveled globally without any audience. The ocean built an acoustic communication infrastructure and then populated it with life that learned to use it. What SOSUS revealed, when civilian scientists finally accessed it, was not a collection of strange anomalies. It was the first complete snapshot of an acoustic ecosystem that had been operating at planetary scale since before mammals existed. We built our eavesdropping system, pointed it at the ocean, and discovered that the ocean had already been doing something far more sophisticated than we were. Part 2 covers what the investigation of that acoustic ecosystem actually found, starting with the answer to Bloop, which turned out to be stranger than the mystery itself, and moving to the animal that has been calling into that ecosystem for 30 years without a single response. The answer to Bloop took 18 years to find. When it finally arrived, in 2005, researchers at NOAA published their conclusion with a relatively quiet announcement. No press conference, no major headline. The conclusion was this: Bloop was an icequake. That word requires unpacking, because most people have never heard it. When a large section of the Antarctic ice shelf fractures, the event produces an acoustic signature, not a crack, an event orders of magnitude larger than a crack. A section of ice the size of a small country suddenly releasing the mechanical stress it had been accumulating for years or decades, breaking along faults that extend hundreds of meters through the ice, sending shock waves through the ice and then through the water below it. The resulting sound enters the SOFAR channel and travels across the ocean exactly the way any other sound does. The frequency signature of a large icequake is biological looking. Ice fracturing produces sounds with organic shapes on a spectrogram, not the clean mechanical signatures of geological rupture, but irregular, variable, living-seeming waveforms. This is why Bloop was initially categorized as likely biological. It wasn't. It was the Antarctic ice sheet speaking, in a language that looked like an animal, because ice and living tissue both fracture in complex, irregular ways. The immediate response from many people who followed the Bloop story was disappointment. The mystery creature, whatever enormous thing people had imagined lurking in the Southern Ocean, didn't exist. The sound had a mundane explanation. The second response, from anyone who thought about it further, was that the actual explanation was considerably more disturbing. Because what icequakes mean is that the Antarctic ice sheet, a body of ice covering 14 million square kilometers, up to 4 kilometers thick in places, holding enough frozen water to raise global sea levels by 58 meters if it fully melted, is so mechanically active that it speaks. It fractures constantly, under its own weight, under the pressure of ice flow, under thermal stress, and those fractures are loud enough to cross entire ocean basins. Bloop was the Antarctic ice sheet, and the Antarctic ice sheet is groaning. The Antarctic ice sheet is not static. It moves continuously. Glaciers flow from the interior toward the coast at rates that vary from meters to kilometers per year, depending on the glacier. Where ice meets the ocean at the coast, enormous shelves of floating ice extend outward over the water. Those shelves flex with ocean swells, accumulate stress from the ice flowing onto them from behind, and occasionally fracture in events that release energy comparable to significant earthquakes. The sound these events produce was, until the SOSUS declassification, essentially unrecorded. Research vessels can't be everywhere at once, and until the hydrophone network was available to civilian scientists, there was no way to monitor Antarctic ice acoustics globally. Once NOAA gained access, the scale of the Antarctic ice sheet's acoustic activity became audible for the first time. The recordings were not subtle. Icequake events of various sizes register on the hydrophone network multiple times per day. Small events produce short, sharp signals. Large fractures produce extended sequences of overlapping signals as the break propagates along a fault line. A single large icequake can generate acoustic activity that lasts for minutes as the fracture chain reacts through thousands of meters of ice. The sound of an iceberg calving, the process by which a piece of the ice shelf breaks off and becomes a free-floating berg, is among the loudest events the ocean records. The acoustic energy released when a large iceberg separates from the shelf and enters the water exceeds the energy of many industrial explosions. The resulting signal enters the SOFAR channel and can be tracked from the moment of calving across the globe as the iceberg drifts and continues to crack and roll and melt over months or years. Every major iceberg has an acoustic signature. The signature changes as the iceberg deteriorates. Large bergs crack internally, develop fracture networks, eventually break into smaller pieces, each transition producing its own sound. NOAA researchers have tracked individual large icebergs acoustically across thousands of miles of ocean, from calving to final dissolution, using only the hydrophone network. The iceberg announces its entire life history in sound, and the SOFAR channel carries the announcement to every listening station in the ocean simultaneously. Bloop was one announcement from one event on one day in 1997. The Antarctic ice sheet has been making announcements like that continuously, every day, for as long as the ice sheet has existed. In 1989, analysts reviewing recordings from a Navy hydrophone array in the Pacific Ocean noticed something unusual. Mixed in with the standard biological signals, whale calls of various frequencies, the background crackling of shrimp colonies, the low rumble of distant geological activity, was a call that didn't match any known whale species. Most large whales call in frequency ranges between 10 and 40 hertz. Blue whales typically call between 10 and 40 hertz. Fin whales call around 20 hertz. Humpbacks operate between 30 and 8,000 hertz in their complex songs. The call in the Navy recording was at 52 hertz, well above the range of all known large whale species, and well below the range of smaller whales and dolphins. The call pattern was unmistakably cetacean. The structure, the timing, the progression, it matched what a whale does when it calls. It wasn't a geological sound. It wasn't mechanical. It wasn't biological noise from any other source. Something was producing a whale call at a frequency no known whale uses. Researchers named it, for lack of anything better, the 52 hertz whale. Over the following years, the SOSUS network tracked the same call, from what appeared to be the same individual, across the Pacific. The whale, if it was a single whale, followed seasonal migration patterns consistent with known large whale behavior, moving between feeding and breeding grounds at the right times of year. It was behaving like a whale. It was sounding like no whale. 30 years of continuous tracking have produced no confirmed visual sighting of the 52 hertz whale. No other whale has ever been recorded responding to its calls. Every migration, every season, every year, the calls go out and nothing answers. The most widely discussed hypothesis is that the whale is a hybrid between two species, most likely a blue whale and a fin whale. Blue whale-fin whale hybrids have been confirmed in small numbers and are known to produce unusual vocalizations, a structural abnormality in the vocal anatomy. Malformed resonance chambers, for example, could also push a standard whale's call up to an unusual frequency. Neither explanation has been confirmed because the animal has never been directly observed. The scientific community is appropriately cautious about the emotional interpretation of this situation. Whether the whale experiences anything that could be called loneliness, whether it is even aware that its calls produce no response, is not something science can determine. What science can say is this: for more than 30 years, across tens of thousands of miles of Pacific Ocean, a single animal has been calling in a frequency that no other animal on Earth is known to hear. The calls continue. Nothing has ever answered. Across the 1960s, the U.S. Navy was inadvertently building one of the most valuable long-term biological datasets ever assembled. SOSUS was recording blue whale calls continuously. When NOAA researchers began analyzing those archived recordings in the 1990s and comparing them to current recordings, they found something that nobody had predicted. Every blue whale population in the world, across the Pacific, the Atlantic, the Indian Ocean, was producing calls at a lower frequency than the same populations had used in the 1960s. Not slightly lower, measurably, consistently, globally lower. The songs were getting deeper, and the trend was continuous. Each decade, the frequency dropped further. This is happening to every blue whale population simultaneously, on every ocean, which rules out any local explanation. Something is driving a global change in how blue whales vocalize, and the trend has been running for at least 60 years. 3 main explanations have been proposed by researchers, and none has been definitively confirmed. The first is population recovery. Blue whales were hunted to near extinction by the mid-20th century, and as their numbers have partially recovered since the 1986 whaling moratorium, individuals may not need to call as loudly or at as high a frequency to find mates, since there are more individuals to hear them. Lower frequency can travel further in the SOFAR channel, so less effort achieves more range. The second explanation is ocean noise pollution. The dramatic increase in shipping traffic, sonar use, and industrial ocean noise since the 1960s has changed the acoustic environment, and whales may have adapted by shifting to frequencies less affected by mechanical noise. The third is climate change. Warming ocean temperatures alter sound transmission properties, potentially requiring frequency adjustments to maintain the same communication range. The honest answer is that researchers don't know which explanation is correct, or whether all three are contributing. What the data shows, without ambiguity, is that blue whales worldwide have been making a coordinated adjustment to how they communicate, and that adjustment has been running continuously for longer than most living humans have been alive. The loudest sound produced by any known living creature is not a whale song. It's a click. Sperm whales produce echolocation clicks, rapid bursts of sound used to navigate and hunt in the complete darkness of the deep ocean, that have been measured at up to 230 decibels at the source. A jet engine at close range produces about 140 decibels. A gunshot at the shooter's ear produces around 160. The threshold for immediate structural damage to human hearing is somewhere around 140 decibels. At 230 decibels, the click of a sperm whale is not just louder than anything else in biology, it's louder than most human-made sounds. At close range, a sperm whale click carries enough acoustic pressure to stun a large fish. Some researchers believe the whales use their clicks offensively, not just for echolocation, but to immobilize prey at short range. The evidence is not conclusive, but the acoustic energy is real. What makes sperm whale acoustics fascinating beyond the raw power is what the click patterns mean. Sperm whales live in social groups, primarily female-based family units, and those groups communicate using sequences of clicks called codas. A coda is a specific rhythmic pattern, a particular arrangement of clicks and silences that functions as a kind of signature. Different groups of sperm whales use different codas, and crucially, young whales learn the coda of their social group from the adults around them. This is a cultural behavior. Codas are not genetically predetermined. They're learned, maintained, and passed on. Different populations in different oceans have different codas that serve as acoustic identification. A sperm whale from the Caribbean uses different patterns from a sperm whale from the Pacific, and researchers studying the recordings can identify the regional origin of a recording by its coda structure. The whales have dialects. They develop those dialects through cultural transmission, not genetics. Before the industrial era, the ocean's acoustic environment was defined entirely by its own inhabitants. Whale calls, geological events, the crackle of biological activity, the wind-driven noise of the sea surface. Background noise levels in the deep ocean were extraordinarily low by modern standards. In the deepest, most remote basins, the ambient sound level approached what engineers call sea state zero, the theoretical quietest condition of the ocean. Then ships got engines. Shipping traffic produces broad-spectrum noise across a range of frequencies that significantly overlap with the frequencies large whales use to communicate. A container ship's propellers and machinery produce continuous, low-frequency sound that propagates through the SOFAR channel the same way whale calls do. Today, the global shipping fleet numbers in the tens of thousands of vessels. At any given moment, there are thousands of ships moving across the ocean, each producing a continuous acoustic signature. The combined effect on the ocean's acoustic environment has been dramatic. Background noise levels in major shipping lanes are dramatically higher than pre-industrial levels. The effective range over which whales can communicate has been reduced, in some frequency ranges, by as much as 90%. A blue whale call that might have been audible to other blue whales 1,000 miles away in a pre-industrial ocean may now be detectable at only 100 miles in a busy shipping corridor because the signal is buried in mechanical noise. Military sonar adds a different category of problem. Mid-frequency active sonar, the type used by naval vessels to detect submarines, produces intense directional sound pulses that are not continuous but reach very high intensities. Multiple documented mass strandings of whales, primarily beaked whale species, have been associated with nearby naval sonar exercises. The leading explanation is that the sonar pulses disrupt diving behavior in ways that cause gas embolism, essentially decompression sickness, when whales surface too rapidly while disturbed. The ocean's acoustic environment is one of the most fundamentally altered aspects of the marine environment, and it receives a fraction of the attention given to more visible forms of ocean change. What we did to the visual and chemical environment of the ocean is widely discussed. What we did to its acoustic environment, the medium through which its largest and most intelligent inhabitants primarily communicate, is understood by relatively few people. Everything covered in Part 2 involves sound produced by living things or by ice, the biological and cryogenic acoustic landscape of the ocean. Part 3 moves into the geological foundations, what fire does to the ocean's acoustic environment, what the seafloor itself contributes, what dawn and dusk sound like in an ocean where thousands of species are calling simultaneously, and what remains in the NOAA archives that still has no explanation. There are sounds in those archives that have been analyzed for decades and remain uncategorized. Some of them may eventually be explained. Some of them might represent phenomena science hasn't fully characterized yet. The ocean is large, deep, and mostly unmonitored, and the hydrophone network, however sophisticated, covers a small fraction of the total volume. What the unexplained sounds represent, whether they're geological, biological, or something else entirely, is a question the ocean hasn't finished answering. There is a sound in the NOAA archives called Upsweep. It was first detected in August 1991, recorded simultaneously by hydrophone arrays across the Pacific Ocean. The sound consists of a narrow, sustained tone that rises slowly in pitch over several minutes, then cuts off. It returns seasonally, stronger in spring and autumn, weaker in the intervening months. Triangulation of multiple recordings places the source somewhere near the Pacific Antarctic ridge, a region of known geological activity along the boundary between two tectonic plates. Researchers have been analyzing Upsweep since 1991. 33 years later, there is no confirmed explanation for what produces it or why it has a seasonal pattern. The seasonal component is the part that doesn't fit any obvious geological mechanism. Earthquakes don't have seasons. Volcanic activity doesn't follow spring and autumn cycles. The seasonal pattern suggests a process driven by something that changes predictably with time of year, ocean temperature, ice extent, biological activity, or some interaction between these factors and geological processes at the ridge. None of the proposed mechanisms has been confirmed. Upsweep is the longest-running mystery in the NOAA sound catalog. It has been recorded continuously for over 3 decades. It has not gotten louder or quieter in any consistent trend. It has not changed its frequency range. It has not stopped. Whatever is producing it has been doing so twice a year, every year, for the entire period during which NOAA has had access to the network, and for an unknown period before that. The ocean is not finished explaining itself. That's where this part begins. Most people locate volcanic activity on land: Vesuvius, Etna, Kilauea, the Cascades. The mental map of active volcanoes is terrestrial. The actual distribution of volcanic activity on Earth is not. Approximately 80% of all volcanic activity on Earth happens underwater, along the mid-ocean ridge system, the network of underwater mountain ranges that extends 65,000 kilometers across the ocean floors. The Mid-Atlantic Ridge, the East Pacific Rise, the Southwest Indian Ridge, these are not quiet geological features. They're active volcanic systems, producing continuous eruptions, building new seafloor constantly, and generating enormous quantities of acoustic energy in the process. The sound of an underwater volcanic eruption is not what intuition suggests. Open-air volcanic eruptions produce a combination of explosion sounds, gas emission, and rock fracturing. Underwater eruptions are dampened by the water column above them. The water absorbs much of the explosive energy. What propagates instead is a series of lower frequency signals, the resonance of steam and gas bubbling through water, the acoustic signature of lava encountering the ocean, the grinding of new rock fracturing as it cools. These signals travel through the SOFAR channel the way everything else does. A mid-ocean ridge eruption on the East Pacific Rise produces acoustic signals detectable on hydrophone arrays in the North Pacific within hours. NOAA researchers have identified multiple previously unknown eruption events in the acoustic archive. Eruptions at seafloor locations where no research vessel happened to be present, documented solely because the eruption entered the SOFAR channel and was recorded thousands of miles away. This has practical value beyond scientific curiosity. Underwater volcanic eruptions can destabilize seafloor slopes, triggering submarine landslides that generate tsunamis. Acoustic detection of eruption events provides early warning capability that visual or seismic monitoring alone cannot match, because the SOFAR channel delivers the acoustic signal faster and with more spatial coverage than traditional earthquake monitoring networks. Hydrothermal vents, the systems of superheated water emerging from the seafloor at mid-ocean ridge locations, produce their own distinctive sound, a continuous hiss and crackle generated by the interaction of superheated water with cold seawater and the precipitation of minerals at the vent opening. In close proximity, the sound has been described by researchers using submersible vehicles as resembling heavy rainfall. That sound propagates into the water column and, for particularly active vent fields, into the SOFAR channel. Vent systems are significant not just acoustically, but biologically. They support entire ecosystems of organisms that derive their energy from chemical reactions rather than sunlight, including the tube worms, clams, and microbial mats that define the vent community. Those organisms produce biological noise of their own, mixing with the geological sound of the vent to create one of the more acoustically complex environments in the deep ocean. Every iceberg begins as part of a glacier or ice sheet and ends as open water. That transition from continental ice to liquid ocean is acoustically violent at every stage. The calving event, when a piece of the ice shelf breaks away and falls into the ocean, produces an acoustic event comparable to a moderate earthquake. The impact of ice on water, the shock waves traveling through both the ice and the surrounding water column, the subsequent rolling of the iceberg as it finds its equilibrium in the water. All of this generates signals that enter the SOFAR channel within seconds and travel globally within hours. As a free-floating iceberg drifts through the ocean, it continues to produce sound. Thermal stress, the temperature difference between the ice surface exposed to sunlight and air versus the ice submerged in near-freezing seawater, causes the ice to crack internally. Ocean swells flex the berg and propagate stress fractures through it. These internal cracks produce short, sharp signals with acoustic characteristics that change as the berg deteriorates. Researchers who study polar acoustics can assess the structural state of an iceberg, how fractured it is, how close to final breakup, from its acoustic signature alone. Large Antarctic icebergs, some of which are the size of small nations, can persist for years or even decades as they drift northward and slowly melt. During that entire period, they produce continuous acoustic activity. Iceberg B-15, which calved from the Ross Ice Shelf in 2000 and was roughly the size of Jamaica, was tracked acoustically across the Southern Ocean for years after it calved. The acoustic record of its drift and gradual dissolution provided data about ocean current patterns in regions where no surface monitoring existed. Arctic and Antarctic sea ice, the seasonal ice that forms and melts each year across millions of square kilometers, produces its own category of acoustic events. Pressure ridges form when wind and current force separate ice flows against each other, crumpling the ice upward in lines that can reach several meters in height. The formation of those ridges is acoustically loud. The cracking and grinding of sea ice under thermal and mechanical stress generates what polar researchers describe as a continuous soundscape, clicking, groaning, hissing, that has no terrestrial equivalent. During polar winters, when sea ice covers maximum area, the acoustic environment of the polar ocean changes completely from its summer state. The ice acts as a barrier between the atmosphere and the ocean, damping out wind-driven surface noise. What remains is the sound of the ice itself, moving, cracking, settling on top of the deeper geological and biological signals from below. At sunrise and sunset, something happens in shallow tropical and subtropical ocean water that has only been systematically studied in the past 2 decades. In coral reef environments, fish and invertebrates that have been inactive overnight begin their day. Thousands of species simultaneously become active, feeding, communicating, and moving. Fish that communicate using sound, and a surprisingly large number of species do, begin calling. Snapping shrimp colonies, which produce continuous crackling throughout the day and night, intensify as activity increases. The combined acoustic output of thousands of organisms transitioning from nocturnal rest to daytime activity produces what researchers have termed the biological dawn chorus, a surge in ambient sound levels that peaks in the first hour after sunrise. The same phenomenon runs in reverse at sunset. The diurnal species quiet down, nocturnal species become active, and a secondary acoustic transition occurs. The ocean has a daily acoustic rhythm driven by the rotation of the Earth and the corresponding shift in available light. This pattern was documented in coral reef environments before being recognized as global. Open ocean research subsequently confirmed that the dawn and dusk transitions are detectable in ambient noise measurements far from any reef system. Zooplankton, the tiny animals that form the base of the ocean food web, migrate vertically each day, moving up toward the surface at night and descending at dawn. That migration, involving trillions of individual animals moving through the water column simultaneously, creates a detectable acoustic signature. The pressure waves generated by mass vertical migration are subtle but consistent, and have been identified in multiple long-term hydrophone recordings. The daily migration of marine life is the largest animal migration on Earth by mass and by number of individuals. It happens every day in every ocean, and it is acoustically visible to sensitive hydrophone equipment. The ocean has a heartbeat, and it runs on a 24-hour cycle. The pistol shrimp story, briefly introduced in the context of Part 1, deserves expansion because it illustrates something fundamental about the ocean's acoustic environment. Biology is not a minor contributor to the soundscape. In some frequency ranges, biology dominates everything else. Pistol shrimp are small, thumbnail-sized, and individually produce sounds that are loud for their size, but not remarkable by ocean standards. In colony formation, however, dense populations of pistol shrimp in warm, shallow water generate collective acoustic output that is extraordinary in its aggregate intensity. The continuous snapping of millions of individuals, each producing a brief, intense pop, combines into a broadband crackling noise that occupies a wide frequency range at significant amplitude. During World War II, this crackling presented a real operational problem for U.S. submarine forces operating in the Pacific. Early sonar systems that Navy analysts used to detect enemy submarines relied on passive listening, recording ambient noise and identifying the mechanical signatures of submarine propellers and machinery against the background. In shallow tropical water, The background noise from pistol shrimp colonies was intense enough to mask submarine signatures entirely. American submarine captains learned to deliberately position their vessels near shrimp colonies when they needed acoustic concealment from Japanese surface vessels using similar passive sonar equipment. The ecological function of this acoustic activity is not entirely clear. Shrimp use snapping as a feeding mechanism. The cavitation event stuns or kills prey. Whether the aggregate noise of a large colony serves any additional communicative or defensive function remains an active area of research. What is clear is that the collective acoustic output of a pistol shrimp colony alters the acoustic environment of an entire reef system in a way that affects every other species present, including those using echolocation to navigate and hunt. Rain on the ocean surface is another underappreciated acoustic phenomenon. When raindrops impact the sea surface, each drop produces a small bubble that oscillates and generates a sound pulse. In heavy rain, millions of these pulses per second produce a characteristic noise that propagates downward through the water column. Hydrophones positioned 100 meters below the surface can clearly detect rainfall above, and the intensity of the acoustic signal corresponds closely to rainfall rate. Researchers have used deep hydrophone arrays as rain gauges, measuring precipitation over remote ocean areas where no surface measurements exist, by analyzing the acoustic signal from below. Lightning strikes on the ocean surface produce a sharp acoustic pulse, detectable by hydrophones at substantial distances. Large sea surface events, ship explosions, aircraft impacts, large meteorite entries, all leave distinct acoustic signatures in the water column. The ocean records everything that touches its surface, and the SOFAR channel carries those records to every listening station simultaneously. Return to the unexplained files. Upsweep has been discussed. There are others that have received less public attention but remain equally unresolved. The train sound, recorded from the equatorial Pacific since 1997, has the characteristics of a geological source. It's continuous, relatively constant in frequency, and shows no seasonal pattern. Several mechanisms have been proposed, including the interaction of large ocean internal waves with seafloor topography in a way that generates continuous acoustic emission. Internal waves, waves that travel along density boundaries within the ocean, rather than at the surface, can reach enormous size, sometimes hundreds of meters in amplitude, and their interaction with the seafloor in shallow areas is known to produce low-frequency sound. Whether this mechanism fully explains train has not been confirmed. Slowdown, the 7-minute descending frequency signal from 1997, remains the most mechanically puzzling. A sound that decreases uniformly in frequency over a fixed duration suggests a source whose acoustic properties are changing systematically. A process cooling, a volume decreasing, a mechanical system running down. What process in the deep ocean would produce exactly that behavior over exactly 7 minutes, once, and not again, has not been identified. The NOAA archive contains additional signals that received less public attention and have been studied less extensively. Some may have straightforward explanations that simply haven't been investigated. Others may represent acoustic phenomena that the scientific community hasn't developed the right framework to interpret yet. The ocean is not fully cataloged acoustically. The hydrophone network, for all its reach, monitors a small fraction of the total ocean volume. Deep basins in the South Indian Ocean, remote areas of the South Pacific, and large portions of the Arctic remain acoustically unmonitored. In those unmonitored regions, whatever acoustic activity exists, geological, biological, or otherwise, goes entirely unrecorded. Sound travels through rock as well as water. The seafloor is not acoustically inert. Geological events produce vibrations that propagate through both the rock of the ocean floor and the water column above it. This means that the acoustic record of the ocean includes not just sounds produced in the water, but signals from the geological structures below it. The sediment that accumulates on the seafloor over millions of years contains a physical record of past acoustic events. Large underwater earthquakes compact sediment. Volcanic eruptions deposit layers of material with different acoustic properties than the surrounding sediment. Significant biological events. The mass sinking of organic material from a large phytoplankton bloom, for example, leave chemical and physical traces in the sediment column. Core samples taken from seafloor sediment are used by geologists to reconstruct the history of Earth's climate, geology, and biology over millions of years. Those cores are, in a sense, acoustic archives. They record the history of events that produced physical changes in the sediment, which includes many of the same events that would produce sounds if the hydrophone network had been in place at the time. The ocean doesn't just transmit sound, it stores a physical record of what has happened over geological time, in a medium that researchers can drill into and read. The relationship between the acoustic record accessible to SOSUS and the physical record preserved in sediment is an area of active research. Cross-referencing real-time acoustic data with geological evidence for past events of the same type allows researchers to extend the acoustic timeline backward beyond the decades covered by the hydrophone network. The ocean has been producing sounds, transmitting them across entire basins, and maintaining a physical record of acoustic events for hundreds of millions of years. The SOFAR channel is not a human discovery. It's a physical property of the ocean that has existed as long as the ocean has had its current configuration of temperature and pressure. Every whale call, every underwater eruption, every iceberg calving, every geological event large enough to generate acoustic energy, all of it has been propagating through that channel, continuously, since before any creature with ears evolved to hear it. What SOSUS and the NOAA monitoring program revealed is that the ocean's acoustic environment is vastly more structured, more complex, and more information-rich than anyone had imagined before instruments capable of listening to it were deployed. The ocean doesn't produce random noise. It produces a layered, multi-source acoustic landscape in which geological, biological, atmospheric, and ice-related events all occupy overlapping frequency ranges, producing interference patterns that change continuously with season, temperature, geography, and the movement of living things through the water. Every sound in that landscape carries information. The frequency of a whale call indicates the species, and in some cases, the population of origin. The duration and intensity of an icequake signal reflects the size and stress state of the ice structure that produced it. The seasonal signature of Upsweep, whatever produces it, encodes information about a process that responds to annual cycles of some kind. The click coda of a sperm whale identifies its social group more reliably than any visual marking. The ocean has been communicating with itself for longer than the word communication has existed. Human beings placed hydrophones in it 80 years ago, listened for submarines for 40 of those years, then handed the recordings to scientists who have spent 30 years trying to catch up with what they missed. The unexplained sounds in the archive aren't evidence that the ocean is mysterious in an unknowable way. They're evidence that the ocean has been doing things at scales and in frequencies that human-scale perception simply wasn't built to detect. The infrastructure to listen is now in place. The question is, how long it takes to understand what's being said. Bloop was answered after 18 years. Upsweep has been running for 33. The 52 hertz whale has been calling since 1989, with no response from any other living thing. The ocean keeps transmitting. Whether we're listening carefully enough to understand it yet is the question that every new deployment of hydrophone equipment, every new analysis of archived recordings, and every unexplained signal still sitting in the NOAA database is working to answer.